Alright, let's look at how we could use mathematical induction for something other than big algebraic equations. So let's do a postage stamp problem. So let P of n be the proposition that one can make exact postage of n cents using only 5-cent and 3-cent stamps. So you've got an infinite supply of 3-cent stamps and an infinite supply of 5-cent stamps. And the question is, what postage can you make or can you not make? For example, if you want to send something that costs 12 cents postage, you could use 4 3-cent stamps. If you want to send something that costs 13 cents, you could use a 5-cent to get 13 cents, you could use 2 5-cents to get 10, and then a 3 to get 13. 14 cents, you could find a combination of 5 and 3 3s, so that's 5 and 9 is 14. So is it always possible to make exact postage using only some combination of 5-cent and or 3-cent stamps? So our proposition P of n says that this is true for postage of n. And we want to prove P of n is true for all n bigger than or equal to 8. And it's 8 because you can't actually find a combination of this that adds up to 7. It just doesn't work. But we can certainly find a combination of stamps that adds up to 8. It's just a 5-cent stamp and a 3-cent stamp. So right away we know that P of 8 is true. If we want to use mathematical induction, here's what we've got to do. We've got to prove that if P of n is true, then P of n plus 1 is true, where n is some number bigger than or equal to 8. If we can prove this, we combine it with this, then we will know that P of n is true for all n bigger than or equal to 8. So all we have to do is prove this implication for some n, right, that if this is true for some n, this will be true for n plus 1. So how do we do that? Suppose P of n is true. So that's our assumption. We can make postage for n cents out of some combination of 5 and 3-cent stamps. The question now is, can we make postage of n plus 1 cents? And the answer turns out to be yes. And we need to consider two cases. Case 1, in making a postage of n cents, we include at least one 5-cent stamp. We include at least one 5-cent stamp. We know we can make postage for n cents. That's what our assumption is, P of n is true. So case 1, the solution we came up with for making n cents included at least one 5-cent stamp. In this case, replace that 5-cent with two 3-cent stamps. Take the 5 off the envelope and instead put two 3-cent stamps in its place. Now this has taken our postage down by 5, this has raised it by 6. Our total postage has gone up by 1 cent. Our original solution gave us n cents postage. This is a solution for n plus 1 cents. So the resulting combination gives postage of n plus 1 cents. And so in this case, where the solution for n included at least one 5-cent stamp, we've shown that we can make postage for n plus 1 cents. But there's another case. Case 2 is in making postage of n cents, we used no 5-cent stamps. one of these cases has to be true. Either we used at least one 5-cent stamp, or we used no 5-cent stamps. Well, if we didn't use any 5-cent stamps, therefore we only used 3-cent stamps. Because that's all we got is 5-cent stamps and 3-cent stamps. If we didn't use any 5, we must have used only 3s. Well, n is bigger than or equal to 8. And we know that for 8 cents we use a 5-cent and a 3-cent. So in this case, n must be at least 9. And if n is at least 9 and we're only using 3-cent stamps, we know we're using at least 3 of these 3-cent stamps. If n is 12, we're using 4. If n is 1200, we're using 400 3-cent stamps. But we know we're using at least 3 3-cent stamps. So we can say we have at least 3 3-cent stamps. Well, my solution here is replace 3 3-cent stamps with 2 5-cent stamps. In other words, remove 3 of the 3-cent stamps from the envelope, replace it with 2 5-cent stamps. Now our postage has gone down by 9 and gone up by 10. Our total postage has gone up by 1 cent. So the resulting combination gives postage of n plus 1 cents. These are the only two possibilities, and in both cases we've come up with a solution that gives us a postage of n plus 1 cents. Therefore, by assuming p of n, we've proven p of n plus 1, where n is bigger than or equal to 8. Therefore, by the principle of mathematical induction, p of n is true for all n bigger than or equal to 8. In other words, it's possible to make exact postage of n cents using only 5 and 3-cent stamps for any n bigger than or equal to 8. Mathematical induction applied to a problem that doesn't involve x's and y's and things like that, but nonetheless is using mathematical induction. And you can prove all kinds of interesting things using mathematical induction. You can prove things in set theory. You can prove things about tiling a square region using L-shaped tiles. You can prove about how many people survive in an odd pie fight where people are throwing pies at each other based on their distance to one another. There's all kinds of applications, and this is central to computer science. The reason this comes up in computer science is because we've done an inductive proof of this proposition, but in doing this proof, what have we done? We've outlined an algorithm for solving the problem of coming up to a solution for p of n. In other words, if you want to make postage of 27 cents, this algorithm tells you how to do that once you know how to make postage of 26 cents. Take the solution for 26, if there's a single 5-cent, replace it with 2 3s, otherwise pick 3 3s, replace it with 2 5s. Well, what's the solution for 26? I don't know. But if you know the solution for 25, this tells you how to get 26. What's the solution for 25? I don't know that either. But if you know the solution for 24, you can get the solution for 25 out of here. You keep working backwards, and you know what? When you get down to 8, I know the solution for 8. It's just 3 plus 5. So, because we have this base case, we know how to solve this for 8. This tells us how to solve it for 9, and once we have that solution, it tells us how to solve it for 10, and so on and so forth. And this is the basis of recursive code. This is why recursive algorithms work, whether you're doing Fibonacci series, or making postage, or anything else. We have a base case, that's the thing that gets you out of your recursive descent, and then we have an inductive step, that's the gist of your recursive code. And it tells you how to solve the current problem based on an earlier version of the problem. And recursion is key to everything we do in data structures. It's how we traverse trees, it's how we perform searches and deletes and things like that in various data structures. So this is really underpinning everything that we do in advanced computer science.